Hello everyone and welcome back to the video series Deep Learning for Teens. In this video, I'll explain what artificial neural networks are. Artificial neural networks are inspired by the human brain, and the human brain contains almost 100 billion cells known as neurons. This is a picture of a typical neuron. It consists of a body known as the soma. The soma has several small branches called dendrites and a long branch known as the axon. The axon has several smaller branches that end with axon terminals. A neuron receives multiple electrical inputs on the dendrites, and based on the inputs, the neuron generates a small electrical output. A neuron is usually connected to many other neurons, and this can be thousands of connections. This diagram shows 3 neurons. If the first neuron has an output as shown by the yellow arrow, that output can make its way to the other neurons that are connected to the first neuron. This is shown with the bigger yellow arrows in this picture. These connections are known as synapses. Synapses can be strong or weak. A strong synapse allows most of the output from the first neuron to go to the connecting neuron. A weak synapse, on the other hand, prevents most of the output from going to the connecting neuron. When we learn, what actually happens is that the synaptic weights between the neurons in our brain change. We can develop artificial neurons that are similar to the neurons in nature. This natural neuron is shown as having 4 inputs. We can make a similar artificial neuron that also has 4 inputs, as shown in the middle. These 4 inputs are connected to 4 weights. The weights represent the synapses in natural neurons and can have a high or low value depending on whether the synapse is strong or weak. The outputs of the synaptic weights are then summed together in the artificial neuron. This sum is then sent to an activation function. I will describe activation functions in a few moments. The result of the activation function is the final artificial neuron output. To help you understand how this artificial neuron works, we will put in some numbers for the inputs and weights. Here, the first input has a value of 0.3, the second input is 0.7, the third input is 0.2, and the fourth input is 0.6. The weights have values of 0.4, 0.9, 0.5, and negative 0.2. Notice that the weights can be negative. The inputs can also be negative. Each input is multiplied by its corresponding weight. So you can see here that input 1 is multiplied by weight 1 as 0.3 multiplied by 0.4. This produces a value of 0.12 that will go to the neuron's summing part. Input 2 is multiplied by weight 2 is 0.7 times 0.9, which gives us 0.63. Input 3 is multiplied by weight 3, which gives us 0.1. Input 4 is multiplied by weight 4, which gives us negative 0.12. In the neuron body, these inputs multiplied by weight values are then summed. In our example, this means we add 0.12, 0.63, 0.1, and negative 0.12, which gives us a result of 0.73. The sum of 0.73 is sent to an activation function. Let's look at what an activation function does. This is a common activation function, known as the sigmoid function. We saw that the input to the activation function was 0.73. We put this on the x-axis of the graph and find where it touches the sigmoid function. At this point, we read the value off the y-axis, which in this case is 0.67. This is the output of the activation function. Putting the sigmoid activation function into our neuron shows that the final output of our artificial neuron is 0.67. Let us take a look at some of the more popular activation functions. We just saw the sigmoid activation function being used in the artificial neural network example. This graph shows the output of the sigmoid activation function for different inputs. Another very popular activation function is the ReLU function. This gives us a 0 for negative inputs, and the output is the same as the input for positive inputs. Another popular activation function is the hyperbolic tangent function. This is usually written as tanh. Finally, another popular activation function is the leaky ReLU. Don't worry if you don't understand these activation functions. When implementing artificial neural networks in software, you simply have to state which activation function you want, and the software will implement the mathematics of the function automatically. Changing the activation function of the neuron usually changes the final neuron output. Here are 2 neurons with the same inputs and weights but different activation functions. The top neuron has a sigmoid activation function and a final output of 0.67. The bottom neuron has the ReLU activation function, and you will see that the output changes to 0.73. We can take this complex diagram of a single artificial neuron and represent it as this form on the right with the single circle. This allows us to represent a large collection of neurons more easily. We will now build up a network of these artificial neurons. Let's assume we have 4 inputs and 2 neurons labeled as N1 and N2. The 4 inputs can be connected directly to neuron 1, as shown by the 4 blue arrows here. Each connection has its own synaptic weight that we represent with the boxes. The inputs can be connected to multiple neurons. In this example, the inputs are also connected to neuron 2, as shown with these orange arrows. The weights are numbered by the input and neuron number. Thus, the weight connecting input 4 to neuron 2 is labeled as W24, as shown by the red box. The 2 neurons, N1 and N2, can be connected to another neuron, N3, as shown in this diagram. To keep the diagrams looking clean, the weight boxes are usually not shown. Just realize that each connection arrow represents a synaptic weight. Each input is usually sent into a single neuron from which it is connected to multiple other neurons. What you see in this picture is usually described as an artificial neural network, and usually abbreviated as an ANN. In deep learning, the ANN usually consists of multiple layers. The layer that the inputs go into is usually called the input layer. The neurons here are called input neurons. The middle layer of neurons is usually called a hidden layer. ANNs usually have multiple hidden layers, as we will see shortly. The last layer of the ANN is usually called the output layer. To make sure you understand how an ANN works, let's look at a simple example network. All the synaptic weights of this network are shown in a box on each arrow. The inputs to this network are shown in red going into the first layer. These inputs go through the input layer and are distributed to the hidden layer of neurons. In the 2 hidden layer neurons, we first multiply each input with its corresponding synaptic weight and then add the multiplication results. This is shown in the big boxes for each of the 2 hidden layer neurons. The neurons then take the sum and pass them through the sigmoid function to generate the final neuron output, which we show in green. The output neuron then takes the hidden layer neuron outputs and does its own multiply and add operation as shown in the box. This value then passes through the sigmoid function to give us the final output of the neural network, which is 0.61. Here is a picture of a more complex ANN. You can see 3 hidden layers. The output layer also has multiple neurons. The output neurons usually represent a type of object the network is trained to recognize. In this example, we have the 4 output neurons representing 4 animals: cats, dogs, cows, and rabbits. So, if we give the picture of a cat as the input to this neural network, you can see that the 4 output neurons each have a separate output value. The output of the cat neuron is 0.9 and is the highest of the 4 output neurons. This means that the network thinks that the input image is a cat. If we change the input image to a rabbit, you can see that the rabbit neuron now has the highest output of the 4 output neurons. This means that the network thinks that the input image has a rabbit in it. Sometimes the ANN can make a mistake, and in that case some other output neuron would have the highest value. This network is often called a classifier network, as it tries to classify the input into one of its output neuron classes. Classifier networks are used very commonly. In the next video, we will develop a simple ANN to recognize handwritten numbers. We will use a database known as MNIST, which has 60,000 images in it. I look forward to seeing you in that video.